In 4.5, we talk about exponential growth and decay in modeling data. So in many situations that occur in ecology, biology, economics, and the social sciences, a quantity changes at a rate proportional to the amount present. In such cases, the amount present at time t is a special function of t called an exponential growth or exponential decay function. So the mathematical model for exponential growth or decay is given by f of t equals a naught e to the kt, or a equals a naught e to the kt. So if k is greater than 0, the function models the amount or size of a growing entity. A naught is the original amount or size of the growing entity at time t equals 0. A is the amount at time t, and k is a constant representing the growth rate. If k is less than 0, the function models the amount or size of a decaying entity. A naught is still the original amount or size of the decaying entity at time equals 0. A is the amount at time t, and k is a constant representing the decay rate. And so you can see what the two graphs would look like. Increasing has a positive looking slope, and decreasing looks like it has a negative slope. So exponential growth and exponential decay. So in 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,052 million. Use the exponential growth model, A equals A naught e to the kt, in which t is the number of years after 2000, to find the exponential growth function that models the data. So our original, which is A naught, is going to be 807. Our final is 1,052, or our A. Between 2000 and 2011, there are 11 years. So our T is 11. And so we want to plug this in so that we can find K, which is our growing factor. So let's go ahead and plug this in. So we have 1,052 equals 807 e to the 11k. We want to get the exponential part by itself, so we're going to divide by 807. So we have 1052 divided by 807 equals e to the 11k. So we can go ahead and take the ln of both sides. So you get ln of 1052 over 807 equals ln of 11k. So the ln and the e essentially cancel, and so you're left with ln of 1052 divided by 807 equals 11k. And so we're solving for k, so we're going to divide both sides by 11. And so k equals ln of 1052 over 807 divided by 11. And let's go ahead and get a decimal approximation. So compute the top first. And you get that K is about 0.02. So let's go ahead and find the formula for it. A equals 807 e to the 0.02 t. We want to be able to plug in any time t and figure out what the population should be. So by which year will Africa's population reach 2,000 million or 2 billion? So in this case, A is equal to 2,000. So plugging into our formula we just found, we have that 2,000 equals 807 e to the 0.02 t. We're going to divide both sides by 807. So we get 2,000 divided by 807 equals e to the 0.02 t. And then we just want to take the ln of both sides. So again, the ln and the e essentially cancel. And we end up with ln of 2,000 divided by 807 equals 0.02 t. And then we're just going to divide both sides by 0.02. And we can go ahead and get a decimal approximation. We get that t is about 45.38 years. And remember that t is the years past 2000. So this will happen in 2045. Let's go ahead and attempt number 2. How long will it take for the money in an account that accrues interest rate at 4.25% compounded continuously to double? So let's just say it doesn't tell us what the original amount is, but we know it needs to double. So let's just say that A naught is $1. So to double $1, my final would be $2. My rate is 4.25%, but this needs to be in decimal form. So 0.0425. And we want to find t. And so we have A equals A naught E to the RT, because this is compounded continuously. And so we have 2 equals 1 E to the 0.0425t. but that's really just 2 equals e to the point 0.0425t. We want to take the ln of both sides. And so the ln and the e end up canceling. And you get ln of 2 equals 0.0425t. And we're going to divide by 0.0425 on both sides. And so let's get an approximation here. That means that t is about 16.31 years. So it would take a little over 16 years for our money to double. And this would work with any amount that you put in, because as soon as you divide, you're always going to get 2. So the half-life of a substance is the time required for half of a given sample to disintegrate. Carbon dating is useful for artifacts or fossils up to 80,000 years old. Older objects do not have enough carbon-14 left to determine age accurately. So use the fact that 5715 years, a given amount of carbon-14 will have decayed to half the original amount to find the exponential decay model for carbon-14. So again, we're not given the original amount, so I'm going to make life easy and say that my original amount is 1, which means that my ending amount, if I have to divide in half for a half-life, would be 1/2. My time is 5,715. And I need to find my function, so I need to find k. So we have a equals a naught e to the kt, and that's 1/2 equals 1 e to the 5,715k, which is really just 1/2 equals e to the 5,715k. So we need to take the ln of both sides. So the e and the ln cancel. Then we have ln of 1/2 equals 5,715k. So to get k by itself, we're going to divide both sides by 5,715. And so let's go ahead and get a decimal approximation here. We get that k is about negative 0.000121. And so my equation would be a equals a naught e to the negative 0.000121t. So in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by a herdsman. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls. So if my original amount is what we're trying to find, we know that the ending was that they had 76% of their original. So that's 0.76 a naught. And so we're just going to plug this in. And figure out how old they were. So this is time. So A is 0.76 A naught. A naught is just regular A naught. E to the negative 0.000121 t. Well, when we divide by A naught, the A naughts cancel on the right and the A naughts cancel on the left. So we have 0.76 equals E to the negative 0.000121 t. We can take the ln of both sides. And so what we end up with is ln of 0.76 equals negative 0.000121 t. And to get t by itself, we're just going to divide both sides by this long decimal. And so t is approximately 2,268.07 years. So this fossil was a little bit above 2,268 years old. Go ahead and pause the video and try the last one for yourself. So the half-life of thorium-229 is 7,340 years. How long will it take for a sample of this substance to decay to 20% of its original amount? So the first thing you have to do is find the K. Once you've done that, then you'll find the T. So let's find the K first. We know that the half-life excuse me, is 7,340 years. So that means that if I plug in 1 gram, then in 7,340 years, I'll have half. And so we end up having 1/2 equals 1 e to the 7,340 k. Let's take the ln of both sides. And so we end up with ln of 1/2 equals 7,340 k. Let's go ahead and divide both sides by 7,340. And so a decimal approximation of k is about negative 0.00000944. And so our equation is A equals A naught E to the negative 0.000944 t. We want to know how old something is when it's decayed to 20% of its original amount. That means that A is 0.2 of A naught. And we're looking for T. So 0.2 A naught equals A naught e to the negative 0.000944 t. And so we're going to divide both sides by A naught. You get 0.2 equals e to the negative 0.000944 t. We'll take the ln of both sides. And so the right-hand side, the ln and the e essentially cancel. And we get ln of 0.2 equals negative 0.000944 t. Our last step is to divide by this really long decimal. And so approximation of t is about 17,049.13 years.